Next, we're going to look at how all this works together, how we actually move through individual processes and threads, move them through the CPU. First, we're going to look at interrupts. An interrupt is a polling process that the CPU performs. Processes and even device drivers are assigned different interrupts, and the CPU polls through these various interrupts to see if there's any work that that particular process or driver requires the attention of the CPU for. So again, this is a polling process, and they're called interrupts. There are maskable interrupts and non-maskable interrupts. If an interrupt is maskable, it means it can be disabled or turned off. So we might allocate more time slices to a particular device by masking its interrupt periodically, which means the CPU doesn't poll that device for several time slices. We might also do this for security purposes, to disable less secure processes from functioning while we're trying to complete a more secure process. Processes are maintained in what's called a process table. This is a table that the system maintains to keep track of the processes that are currently being managed by the operating system. Remember, truly, only one process can only have one thread being worked on at any point in time. So we have to keep track of all the processes while they're waiting their turn in the CPU itself. When we accept a process from an application, the system allocates resources to that process. One of those resources lives in a piece of memory, and we call this memory location for the process a stack. A stack provides that process the resources that it has requested. Resources are the amount of memory for instructions and data input, so that when the process finally gets its turn in the CPU, it has all these components together so the control unit can slip these details into the CPU and actually have the instruction be worked upon. Here's an example of an application. At the top we see the application has 5 components going into a stack. Let's imagine that components 3, 4, and 5 from the application are data bits. They're variables that are plugging into some algorithm. The algorithm being the instruction, a thread, and that would be input number 2. So the instruction is number 2, and then we have 3 variables or pieces of data that the instruction is actually going to perform work upon. The last piece of input, the item number 1 coming from the application at the top, is a return pointer that says, when this particular instruction is completed, what do I do next? We see that the instruction and the data then flows into the CPU, the purple box to the right called the procedure. That's the CPU actually performing the work, and then down below, after that work has been completed, the CPU informs the stack that this work is now accomplished. What do we do next? And you see the instruction go back to the return pointer, and the return pointer feeds back to the application and says, all right, this particular stack has accomplished its task. So again, the stack is a register or area of memory that is allocated to the process, and we keep a process table that maintains a list of all the stacks and what the work is that's being done on those. Again, when the process has completed its turn in the CPU, the CPU sends an instruction or a flag back to the stack that says this work is done. Now the return pointer identifies where to move to next. As the process is actually being filed into the CPU, there is also something called the stack pointer that keeps track of the individual discrete data components that are moving into the buffer memory, the registers, that the CPU is then going to be working upon.